Hello hackers, in this video, we are going to discuss about networking protocols for hackers. Before deep dive into realm of networking protocol, please subscribe to our channel. A click is really helpful us to bring great content for you, and we also have a short disclaimer for you guys. Disclaimer: it is important to emphasize that hacking into computer networks, systems, or devices without proper authorization is illegal and unethical. The information provided here is solely for educational purposes and should not be misconstrued as encouragement or support for illegal activities. Let's begin with IP addresses. An IP address, short for Internet Protocol Address, is a numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. It serves as a unique identifier for identifying and locating devices on a network. IP addresses are essential for routing data packets across networks, enabling devices to communicate with each other. For example, consider a home network with multiple devices, such as computers, smartphones, and printers. Each device on the network is assigned a unique IP address. When a user wants to send an email from their computer to a friend's smartphone, the email client uses the friend's smartphone IP address to route the message across the network. Similarly, when a user accesses a website, their device uses the website IP address to locate and retrieve the requested web page. In essence, IP addresses play a crucial role in facilitating communication and data exchange between devices on a network, allowing for seamless connectivity and interaction across the Internet. Public and private IP addresses. Public and private IP addresses serve different purposes in networking. A public IP address is globally unique and is assigned to devices directly connected to the Internet, allowing them to communicate with other devices on the Internet. On the other hand, private IPv4, which has 4.3 billion IP address, which are not enough to serve over 8 billion peoples on the planet. So this IP is used within a private network, such as a home or office network, and is not directly accessible from the Internet. These are used in local area network, which is also called LAN. Instead, private IP addresses are typically assigned by a router to devices within the network, enabling communication between devices within the same local or network. For example, a home router might assign private IP addresses like 192.168.1.2 or something else. Start with 192, which are private range. We will discuss private ranges in classes later on. For example, when a computer with a private IP address, such as 192.168.1.2, requests a web page from a server on the Internet, the router replaces the source IP address in the outgoing packets with its public IP address, such as 203.0.113.5 or different in your case. The server responds to the request by sending data packets to the router public IP address, and the router uses the NAT mapping table to forward the response to the original device with the private IP address. In this way, NAT enables devices with private IP addresses to access resources on the Internet without requiring each device to have a unique public IP address, conserving IP version for address space and enhancing network security. There are three ranges in order like A, B, and C classes. In class A, the range of private IP addresses start with 10.0.0 and ends with 10.255.255.255. In class B, addresses starts with 172.16.0.0 and ends with 172.16.255.255, and class C ranges starts from 192.168.0.0 and ends with 192.168.255.255. It's assigned to computers, smartphones, and printers within the home network or local area network. These devices can communicate with each other using their private IP addresses but rely on the router public IP address to access resources on the Internet. Public IP addresses facilitate Internet communication, while private IP addresses enable communication within a local network. Next protocol is NAT, Network Address Translation Protocol. It is a crucial technology that enables devices with private IP addresses to communicate with the Internet by converting their private IP addresses to a public IP address. NAT operates at the router level, where it maintains a mapping table that associates private IP addresses from devices within a local area network. When a device within the local network initiates communication with a destination on the Internet, the router modifies the source IP address in the outgoing packets from the device private IP address to its own public IP address. This process allows the device to send requests to Internet destinations using the public IP address, ensuring that responses from the Internet are routed back to the correct device within the local network based on the entries in the NAT mapping table. Our next protocol is ARP, or Address Resolution Protocol. It plays a crucial role in facilitating communication within a local area network by mapping IP addresses to MAC addresses. In a LAN environment, devices communicate using MAC addresses, which are unique identifiers assigned to each network interface card. However, when a device wants to communicate with another device using its IP address, it needs to know the corresponding MAC address to send data packets. This is where ARP comes in. When a device wants to communicate with another device on the same LAN, it first checks its ARP cache to see if it already knows the MAC address corresponding to the IP address of the target device. If the MAC address is not found in the cache, the device sends out an ARP request broadcast packet to the entire LAN network, asking them who has this IP address. The device with the corresponding IP address then responds with its MAC address, allowing the requesting device to update its ARP cache with the MAC address of the target device. Once the MAC address is obtained, the devices can communicate directly using data link layer protocols without the need for further ARP requests. ARP is essential for smooth communication within the network, but it is also a potential target for hackers who might be able to manipulate ARP. Request attacker sends fake ARP messages over a local area network. These messages associate the attacker's MAC address with the IP address of a legitimate device on the network, such as a router or a server. As a result, traffic intended for the legitimate device is redirected to the attacker system. It is also called man-in-the-middle attack. Now, next one is DHCP, or Dynamic Host Configuration Protocol. Simplifies the process of assigning IP addresses to devices on a network dynamically. When a device joins a network, it sends out a DHCP request broadcast packet, seeking an IP address. A DHCP server on the network receives this request and allocates an available IP address from its pool to the requesting device. Additionally, the DHCP server provides other network configuration information, such as subnet mask, default gateway, DNS server addresses, and lease duration. Once the device receives this information from the DHCP server, it configures its network settings accordingly and becomes fully connected to the network. For example, when a new computer connects to a home router, the router acts as a DHCP server, assigning an IP address like 192.168.1.2 along with other necessary network settings to the computer. This dynamic allocation of IP addresses by DHCP eliminates the need for manual configuration, making network management more efficient and scalable. Let's dive into IP header. The Internet Protocol header, or IP header, is a fundamental component of data packets used in Internet communication. It contains essential information for routing and delivering packets across networks. The IP header typically includes fields such as the source destination and along with destination IP addresses, which identify the sending and receiving devices, respectively. Additionally, it may include fields for packet fragmentation, time to live auth TTL, type of service or TOS, and checksum for error detection. The IP header serves as the envelope for the data packet, providing the necessary addressing and control information for successful transmission and delivery over the Internet. TCP Transmission Control Protocol, or TCP, is a core communication protocol in computer networks, providing reliable, connection-oriented data transmission between devices. TCP ensures data integrity and order through mechanisms like acknowledgements, sequencing, and flow control. It establishes a connection between sender and receiver through a three-way handshake, manages data transmission in segments, and guarantees delivery by retransmitting lost or corrupted packets. TCP also handles congestion control to prevent network overload. Once data transmission is complete, TCP terminates the connection gracefully. This robust protocol underpins many Internet applications, such as web browsing, email, and file transfer, ensuring efficient and dependable data exchange across networks. The Transmission Control Protocol segment, often used for reliable communication, features control flags including SYN as synchronize, ACK as acknowledge, FIN as finish, and RST as reset. SYN flag initiates a connection, ACK flag are going to acknowledges received data, FIN flag indicates the end of data transmission to finish a TCP connection, and RST flag is going to resets or aborts a connection. These flags orchestrate the TCP handshake, data transfer, and connection termination, ensuring orderly and reliable communication between devices over the Internet. Three-way handshake. The three-way handshake is a fundamental process in establishing a TCP connection between two devices on a network. It involves three steps. First, the client sends a SYN packet to the server, indicating its desire to initiate a connection and including an initial sequence number. The server responds with a SYN and ACK packet, acknowledging the client request and also sending its own initial sequence number. Finally, the client sends an ACK packet back to the server, confirming receipt of the server response and completing the connection establishment. This process ensures reliable communication between the client and server by synchronizing sequence numbers and establishing a reliable channel for data transmission. For example, when a user sent requests through web browser for a web page from a server, it initiates a three-way handshake by sending a SYN packet. The server responds with a SYN and ACK packet, and upon receiving it, the browser sends an ACK packet to complete the connection, allowing the web page to be transmitted securely. Now move on. UDP User Datagram Protocol is a connectionless and lightweight transport layer protocol in the Internet Protocol Suite. It provides a simple and unreliable delivery mechanism for data packets, making it suitable for applications where speed and efficiency are prioritized over reliability, such as real-time streaming, voice over IP, and online gaming. Unlike TCP, UDP does not establish a connection before sending data and does not guarantee delivery or order of packets. This simplicity allows UDP to transmit data quickly without the overhead of connection setup, acknowledgement, or retransmission mechanisms. However, because UDP lacks error checking and flow control, applications using UDP must handle packet loss, duplication, and out-of-order delivery at the application layer. Despite its limitations, UDP remains essential for scenarios where low latency and high throughput are critical requirements. Some of the key protocols that use UDP include DNS, SNMP, or NTP. We will discuss these protocols along this video. DNS, or the Domain Name System, is a fundamental component of Internet communication, translating human-readable domain names into numerical IP addresses used by computers to locate resources on the Internet. When a user inputs a domain name like google.com into a web browser, the DNS protocol facilitates the resolution process by querying a series of DNS servers to obtain the corresponding IP address. For instance, if a user types www.google.com into a browser, the DNS resolver sends a request to a DNS server, which recursively queries authoritative DNS servers until it obtains the IP address associated with google.com. Once resolved, the browser then establishes a connection to the server hosting the website. DNS protocol acts as the Internet address book, translating human-readable domain names into machine-readable IP addresses to facilitate seamless communication and access to online resources. One common attack on DNS is DNS enumeration. DNS enumeration involves querying DNS servers to gather information about a target network, such as valid domain names, associated IP addresses, mail servers, and more. Hackers leverage DNS enumeration to gather reconnaissance data that can aid in identifying potential vulnerabilities and targets for further exploitation. By understanding the network infrastructure and domain structure, attackers can craft more targeted attacks, such as social engineering, phishing, or DNS spoofing. Now we have ICMP protocol, the Internet Control Message Protocol. It is a network layer protocol used for diagnostic and error reporting purposes in IP networks. ICMP messages are typically generated in response to errors in packet transmission or to provide information about network status. For example, when a packet cannot reach its destination due to network congestion or a routing issue, an ICMP message such as destination unreachable is sent back to the source. Another common ICMP message is echo request and echo reply, which are used for the famous known ping utility, where a device sends an ICMP echo request message to another device, and the receiving device responds with an ICMP echo reply message to indicate its availability and responsiveness. Overall, ICMP plays a crucial role in network troubleshooting and management by facilitating communication between network devices and reporting on network conditions. SNMP, Simple Network Management Protocol, is a protocol used for network management and monitoring of network devices. SNMP operates by allowing network administrators to monitor and manage network devices remotely. SNMP uses a manager-agent architecture, where SNMP managers collect information from SNMP agents running on network devices. SNMP agents maintain and report information about the device configuration, performance, and status. The SNMP manager can issue requests to retrieve information or configure settings on the agents. For example, an SNMP manager could query an SNMP agent on a router to retrieve information about network traffic, such as bandwidth usage or interface status. SNMP is widely used in its environments to monitor and manage network infrastructure, making it an essential tool for network administrators. SMB, the Server Message Block Protocol, is a network file sharing protocol used to provide shared access to files, printers, and other resources on a network. SMB operates on TCP ports 445 and 139 and facilitates communication between client and server systems. One of the most common implementations of SMB is Microsoft implementation, known as Microsoft SMB. With SMB, users can access files and resources stored on remote servers as if they were local, allowing for seamless collaboration and file sharing within a network environment. For example, in a business setting, employees can access shared folders hosted on a file server using SMB to collaborate on documents, share project files, or print documents to network printers. Additionally, SMB supports authentication and access control mechanisms to ensure secure access to shared resources, allowing administrators to control who can access which files and folders. Overall, SMB plays a crucial role in facilitating efficient and secure file sharing and resource access within networks of all sizes. FTP, File Transfer Protocol, is a standard network protocol used for transfer files between a client and a server on a computer network. FTP operates on the client-server model, where the client initiates a connection to the server to perform file transfers. It typically utilizes two separate channels, a control channel for sending commands and receiving responses, and a data channel for transfer actual file data. Users authenticate themselves with a username and password to access files on the server. For example, using an FTP client software like FileZilla, a user can connect to an FTP server by entering the server hostname, username, and password. Once connected, the user can navigate directories, upload files from the local machine to the server, and download files from the server to the local machine. FTP is widely used for website management, software distribution, and file sharing purposes. POP, Post Office Protocol, is an email protocol used by email clients to retrieve messages from a mail server. There are two main versions, POP2 and POP3. POP works by establishing a connection between the email client and the server, typically over TCP port 110. Once connected, the client authenticates itself with the server using a username and password. After authentication, the server allows the client to access and download any new email messages stored on the server. The messages are typically downloaded to the client device and removed from the server, although some configurations may allow messages to be retained. For instance, when a user accesses their email using a desktop email client such as Mozilla Thunderbird, the client connects to the POP server, authenticates, and downloads new email messages to the user local inbox. Telnet. Telnet is a network protocol used for remote terminal access to another device over a network. It allows a user to establish a virtual terminal connection with a remote host, enabling interactive communication and command execution as if the user were physically present at the remote device. Telnet operates on TCP port 23. For instance, a user can use a Telnet client to connect to a remote server by specifying the server hostname or IP address. Once connected, the user can interact with the remote system command line interface, execute commands, and retrieve information. However, Telnet transmits data, including login credentials, in plaintext, making it insecure for transmitting sensitive information over untrusted networks. Therefore, it is often replaced by more secure protocols like SSH or Secure Shell. However, it still finds utility in certain scenarios, such as remote administration of legacy systems or network device configuration. For example, a network administrator might use Telnet to access and configure network switches or routers remotely. To establish a Telnet session, a user initiates a connection to the remote server using Telnet client software, typically by specifying the server IP address or hostname. Once connected, the user can interact with the remote system by entering commands and receiving responses in real time, enabling tasks like troubleshooting, configuration, or software management. SSH, the Secure Shell Protocol, is a cryptographic network protocol used for secure communication over an unsecured network. It provides strong encryption, authentication, and integrity protection, making it suitable for securely accessing remote systems and transferring data. SSH operates on TCP port 22 and consists of two main components, the SSH client and the SSH server. When a user wants to establish a secure connection to a remote system, they initiate an SSH session by specifying the remote hostname or IP address along with their username and authentication credentials. For example, using a terminal or SSH client software like PuTTY, a user can connect to a remote server by running the command SSH username at the rate remote host. Upon successful authentication, the SSH server grants the user access to the remote system command line interface or provides a secure tunnel for other network services. SSH protocol ensures confidentiality by encrypting all data exchanged between the client and server, integrity by verifying data integrity during transmission, and authenticity by using cryptographic keys for user authentication. Overall, SSH is widely used for secure remote administration, file transfers, and tunneling services, offering a robust solution for protecting sensitive communications over the Internet. There is another secure protocol which operates over the Internet called SSL, which stands for Secure Sockets Layer. It is a cryptographic protocol designed to provide secure communication over a computer network, typically the Internet. It operates by establishing a secure connection between a client and a server, ensuring that data exchanged between them remains confidential and tamper-proof. SSL utilizes encryption algorithms to scramble data during transmission, making it unreadable to unauthorized parties who might intercept it. Additionally, SSL provides authentication mechanisms to verify the identity of both the client and the server involved in the communication, thereby preventing man-in-the-middle attacks. SSL is commonly used to secure sensitive transactions conducted over the Internet, such as online banking, e-commerce purchases, and login sessions to secure websites. For example, when a user accesses a website with an SSL certificate installed, their browser and the website server establish an encrypted connection, indicated by the HTTPS prefix and a padlock icon in the browser address bar. This encryption ensures that any data exchanged, such as login credentials or payment information, remains protected from eavesdropping or manipulation by malicious actors. Overall, SSL plays a crucial role in safeguarding the confidentiality, integrity, and authenticity of online communication, contributing to a more secure internet browsing experience for users worldwide. TLS Transport Layer Security. It is a cryptographic protocol used to secure communication over computer networks, most commonly the Internet. It operates at the transport layer of the OC model, providing encryption, authentication, and data integrity for data exchanged between client-server applications. TLS ensures that sensitive information such as login credentials, personal data, and financial transactions remain protected from eavesdropping and tampering by malicious actors. TLS works by establishing a secure connection between the client and server through a process called the TLS handshake. During the handshake, the client and server negotiate encryption algorithms and exchange cryptographic keys to encrypt and decrypt data. Once the secure connection is established, data transferred between the client and server is encrypted, ensuring confidentiality. Additionally, TLS provides mechanisms for verifying the identity of the server and, optionally, the client, thus preventing man-in-the-middle attacks. TLS is widely used in various applications, including web browsing, email, instant messaging, and virtual private networks or VPN to safeguard sensitive information and ensure secure communication over the Internet. HTTP. Hypertext Transfer Protocol. It is the foundation of data communication on the World Wide Web. It serves as a protocol for clients such as web browsers to request web pages and other resources from servers across the Internet. HTTP operates on a request and response model, where a client sends a request to a server, and the server responds with a requested resource, typically a web page. This communication occurs over TCP and IP, with HTTP messages consisting of a header and an optional body containing data. The header includes details like the HTTP method such as GET or POST request, the URL of the requested resource, and various metadata. For example, when a user types a URL into their web browser, the browser sends an HTTP GET request to the server hosting the website, asking for the specified web page. The server then responds with the requested web page, along with an HTTP status code indicating the success or failure of the request. HTTP forms the backbone of the modern web, facilitating the seamless exchange of information between clients and servers, enabling users to access a vast array of resources and services online. HTTPS. Hypertext Transfer Protocol Secure. It is a secure version of the HTTP protocol used for transmitting data between a web browser and a website. It provides encryption and authentication mechanisms to ensure the confidentiality, integrity, and authenticity of data exchanged over the Internet. HTTPS operates over Transport Layer Security, or Secure Sockets Layer called SSL, which encrypts the data transmitted between the client and server. This encryption prevents unauthorized parties from intercepting and reading sensitive information, such as login credentials, personal data, or financial details during transmission. For example, when a user accesses a banking website to log in to their account, the browser establishes an HTTPS connection with a bank server. The server presents its digital certificate, which the browser verifies to ensure it is authentic and issued by a trusted certificate authority or CA. Once the connection is established, all data exchanged between the user browser and the bank server is encrypted, safeguarding it from eavesdropping or tampering by malicious actors. In summary, HTTPS is essential for securing online transactions, protecting user privacy, and maintaining trust in web communications. In this video, we will use and discuss some of the most essential networking protocols, which are very useful for hacker or security professional. Thanks for watching this video. Please like, share, and comment down below if you want a video on a specific topic, which are around to your head. Do not hesitate. See you in the next one.